continue our discussion on this wind turbine rotor dynamics. So, what we have discussed or completed so far, the basic principle from here, the different types of loads, and then how the loads impact the rotor dynamics. So, what we want to talk about is that this wind turbine rotor dynamics, how this imposed loads and dynamic interaction produces forces and motions in wind turbines. So that's what we are talking about this wind turbine rotor dynamics. These are important to understand this imposed uh, load and dynamic interaction, so which produces forces and motions, and that is required for design process. Okay, so the effects of all types of load, whether static, steady, cyclic, transient, impulsive, stochastic, that one has to determine. So all types of loads need to be determined. Okay. So what we are going to do here is that we are going to analyze the forces and motions which are to be considered. So we start with a rigid rotor model, and then we would develop the linearized system. Now, so the loads in an ideal rotor, um, loads in an ideal rotor, the most important rotor loads are with first on the blades and torque drive the rotor. So obviously, when you try to model the rotor as a simple rigid, aerodynamically ideal rotor to be useful to get a feeling for steady loads on an wind turbine. So uh, uh, so the primary thing is that, let's say, if you talk about thrust, which we have already estimated as CT rho I R square and U square. So CT would be thrust coefficient, rho is the density of air, okay, radius of rotor, and U infinity, or whatever you call it, free stream velocity. For ideal case, CT is 8/9. So obviously, in terms of this simple model, then the total thrust on a so in terms of simple model, mm, the total thrust on a given rotor varies only with the square of wind speed. So that's number one. Number two, we have bending moments and stresses. So the bending moments are, or one can say the blade bending moment are usually treated as either stepwise or easewise. So when you talk about the stepwise bending moments that cause the blades to bend upwind or downwind. Okay, and so this is something, well, the blade uh, getting the movement due to this flapwise motion. The other one could be easewise bending moments. So these are parallel axis, and this give rise or producing torque. So these are sometimes referred as lead lag. Lead lag. So that means you can have this. I mean, we have already shown the flapwise movement, um, and for that also the if you have moments and then along with the rotation that steepens. So from simplified picture, we have kind of seen that. So that is one thing, flapwise moment. Then you can have easewise moment, which is parallel to the rotor axis. That means this is the rotor axis, then there would be parallel to that. So that means moments are kind of like this, which is going to be kind of an. So if you look at this view, then it is having a motion like that. So this can be referred as a lead lag. Uh, so this also gives rise to some kind of an or producing torque. So these are bending moments and stresses that um, now we have some kind of an axial forces and moments. Okay, the flapwise bending moment, the flapwise bending moments or moment at the ideal blade of a turbine with multiple blades given by product of the thrust force per blade and 2/3 of radius. This let's consider the rotor as made up of a series of concentric annuli of with dr. Flapwise bending moment, single blade, let's say m beta, for a turbine with d number of blades can be written as m beta 1 by b 0 to r 5 8 by 9 used to r dr. If we integrate this term and gather this, so upon integration and gathering terms, so what we get is that m beta equals to t by b 2/3 r. So this is the flapwise bending moment on a single blade. Okay. I mean, if you multiply by the beta, then total flapwise bending moment found out. So what we can estimate is that maximum flapwise stress So the maximum flap wise stress, which is sigma beta max, due to bending at the root, which we can write as sigma beta max m beta into c IB. Here c is the distance from the flapwise neutral axis. IB is the area moment of inertia of blade cross section at the root. This is how one can find out the maximum flapwise stress. So you can see this term here. This is the same as incremental normal force. Okay, and here the script beta, so normal force, and subscript beta here blade deflection angle, blade deflection in the flap direction. Flap direction. Okay. So this is used to emphasize the have a continuity between hinge spring that we are going to talk in the subsequent discussion. Now, like maximum flapwise stress, so the shear force A sub beta in the root of the blade, so can be estimated like the thrust divided by number of blades. So what it talks is that if I have to summarize this uh, uh, flap forces and moment, when ideal rotor, bending forces and stresses vary with the square of the wind speed and independent of blade angular motion or position, which is azimuthal. So the blades on rotors designed for higher tip speed ratio operation, smaller chords and cross-sectional area moment of inertia. So they experience higher flapwise stress. So this is what one can. So essentially in summary, one can say for a given ideal rotor bending forces and stresses vary with u square and of blade angular position. Also, blades on rotors tip speed ratio operation have smaller cross-sectional area moment of inertia. So they experience higher stresses. Okay, so that's what happens with flapwise bending moments. Now we can similarly edgewise forces and moments can be estimated. So as already mentioned that uh, edgewise moments give rise to the power producing torque. Hmm. So in terms of blade strength, aerodynamic edgewise moments are generally of less significance than their flapwise counterparts. So mostly the flapwise motions or the forces for that the stresses or the moments that are created they are quite predominant that than edgewise motion. Yeah. Uh, but one thing one has to take into consideration that during operation for certain, I mean, for sometimes, or it may possibly happen is that the these edgewise motions or the moments due to the blade's own weight can be significant and may have significant impact on the overall forces or moments that's uh, acting on that turbine. So this is something we also need to look at it, that how one would estimate these edgewise forces and moments and things like that. That will continue in the next session.